Okay, so on this presentation, we're going to talk about a specific type of circuit and paths that some of our graphs have. They are called Euler circuits and paths, and this came up in the early 1700s. They were trying to decide how they could get across all 7 bridges that joined various parts of the city without crossing a bridge more than once, and their stroll through the city. So this is kind of what the layout looked like. There was 7 bridges, and they wanted to stroll through the city and cross the bridges once and only once. So we can make a graph from this diagram with the vertices representing the landmasses and the edges representing the bridges. And then our goal is to cross each of those edges, which are our bridges, once and only once, and end back up where we started. And that would be a Euler circuit. So by definition, a Euler circuit is a circuit, which remember a circuit has the same start and end point. So it's a circuit that passes through every single edge of the graph and ends back up at the same starting point. You can only use the edges once and only once. Now, not every graph has a Euler circuit. 2 of the requirements for whether or not it has a Euler circuit comes from our Euler circuit theorem. The first is the graph has to be a connected graph. And remember, the definition for a connected graph is you have to be able to get to every single one of the vertices on the graph, and every vertex has to be even. Even meaning it has to have an even degree. The degrees at each of the vertices has to be even. And if that's the case, then you have at least one Euler circuit. Usually there's a lot more than just one Euler circuit, but there is at least one. If the graph has any odd vertices at all, then it does not have a Euler circuit because all of the vertices have to be even. So first, in order to determine whether or not a Euler circuit exists, you have to first see if the graph is connected. If it's not a connected graph, you can move on because there is no Euler circuit. However, if it is a connected graph, then check the degrees of each of the vertices. If you hit a vertice that is odd, then you do not have a Euler circuit. If there are no odd vertices, then yes, your graph has a Euler circuit. So let's look at this example here. I have this graph that you see on the screen, and we want to prove by counting the vertices that this figure has a Euler circuit. So we need to first determine if it's connected. It is a connected graph. Let's check the degrees of each of the vertices. The degree right here at A, vertex A has a degree of 4, that's even. Vertex B also has a degree of 4, that's even. Vertex C has a degree of 4, that's also even. And vertex D has a degree of 6. That's also even. So this is a connected graph, and all of the vertices are even. Therefore, a Euler circuit does exist. If I wanted you to find the Euler circuit, then you would first identify your start and end point, and that can be any vertice as long as you label it. So you would label your start and end point, and then you would travel through each of the edges once and only once. You can repeat the vertices, but you cannot repeat the edges. And we could go through each of the edges once and only once and end right back up where we started at. So I'll include on the next video how I expect for you to document that, but this graph does have a Euler circuit, and we'll stop there for now.